so much. And thanks to the folks at SMMR for hosting the webinar today and the invitation. I'm excited to present some work measuring ocean ecosystem wealth in the context of global change and conflict. A little bit about myself. I'm an economist. I'm a senior lecturer at the University of Exeter Business School in the Department of Economics and a member of the LEAP Institute, Land, Environment, Economics, and Policy Institute, hosted there as well. This is, if I can make sure that the slide changes. This is a part of a project called Future Fish Wars, Chasing Ocean Ecosystem Wealth. And these are some of the wonderful collaborators that I have the privilege of working with from across the US at Oregon State University, Cornell, WWF, and the Peterson Institute for International Economics, with also a great team of collaborators and folks whose work I'm going to discuss today and preview, including wonderful postdocs, including Pedro Barros and John Woodill, whose work I'll talk about in a little bit as well. This work was a large funded project with 6 work packages looking at the intersection of conflict, climate change, and fisheries, where we asked the question whether climate change will give rise to, quote, future fish wars. And I say was because, unfortunately, this is the close of the project due to the current academic funding climate in the US. So our grant has been canceled as of the beginning of this month through the end of last month. And so unfortunately, this is a way to capture some of the great progress that we've made and summarize some of this work in order to look ahead at other sources of funding and other sources to continue this important work on understanding conflict, climate change, and fisheries, which represent the primary food source for about 1 billion people on the planet. So with that out of the way, what I'm going to do today in the next 50 minutes or so is talk about why we should think about ocean wealth, ocean accounts, and sustainability. I'm going to review an asset pricing method for understanding nature as a form of capital. I'm going to then evaluate the management of a marine fishery in the context of this wealth accounting framework so that we have an apples to apples comparison of how we should treat investments in a sustainable ocean economy as compared to investments that one might make if one were looking at the balance sheet of a business, company, or nation. I'll discuss extensions to existing natural capital asset pricing theory that we made progress with through this project, and then look forward to simulate heterogeneity in a 2-actor, 1-stock fisheries model for the Gulf of Mexico, and also look forward to future work with Bering Sea and Aleutian Islands pollock, which is the case in Alaska in the US. So to kick off with some motivation, climate change is reallocating natural capital. We know that we're going to experience and are experiencing increased storm frequency and intensity with global change. We also know that temperature-mediated species range shifts are manifesting for many important species on the planet today. The figure on the top right represents the movement in the median of populations of fluke and hake northward along the US East Coast that was featured in a paper by Eva Papaioannou et al. In 2021. These, what I'm calling climate-induced wealth changes or transfers, where natural resources are moving latitudinally with temperature gradients, may not be zero-sum. It's not just a transfer of the same bank balance from one entity to another, but there might be loss in the reallocation of capital due to frictions and other phenomena. One of those we're going to talk about to motivate a multi-actor natural capital asset pricing framework. The 3 examples on the bottom represent another stream of research I'm interested in, which is how climate change reallocates kind of coastal natural capital. And here I'm talking about sand. So on the left and the bottom part of the figure, you can see how the natural flow of sand along the coast of Florida from north to south is interrupted by a produced capital cut through the coast. That's an inlet or a port. And that changes the allocation of sand, valuable recreational beach space, along the gradient from north to south, resulting in accretion of sand and wide beaches on the north and erosion of sand and erosion threats to the south. And I believe that's a photo from Port Everglades in 2018. To combat some of these natural wealth allocation mechanisms that happen via, say, natural currents that are mediated by human intervention, we can undertake projects to adapt to these situations. The middle picture in the bottom, paying for sand to be reallocated along the coast via beach dredge and fill. But we also have some natural solutions to these problems. And the picture on the right represents the ability of natural vegetation to help combat erosion and to encourage accretion along coasts. So there is a range of problems that are caused by kind of the interaction of produced and natural capital, of human intervention. There are some technological or produced capital solutions, but there's also value in natural capital that might substitute for some of the produced capital solutions or some of the man-made interventions to correct the problem of wealth changes induced by natural systems. And for climate, that might be super, super important. As I mentioned, these wealth transfers might not be zero sum, which in the context of the movement of fisheries along a coast where we have different property rights regimes might mean that the loss in value of fisheries that are generally fished by one population might be greater than the gain in the value of fisheries fished by a population to the north that doesn't have, for example, the technology, the expertise, or the information, or the institutions to be able to as effectively use the resource. The resource could also depreciate with that climate-induced change, moving to a habitat that's less suitable. And I'll talk about a couple of different outcomes that we hypothesize in the kind of set out of this project next. So here, we think that the value of natural capital depends on the context in which it happens. And here, in terms of context, we think about location and institutions as the key drivers of spatial heterogeneity or differences across space in the value of natural capital. These non-zero sum climate-induced wealth transfers or changes in the value of capital as it moves from one place to another might happen simply as the result of a fish fin crossing a border or an exclusive economic zone. The first thing we think might happen under different climate regimes is what we're calling value asymmetry. Here we refer to value asymmetry as what happens when an asset moves across a border from nation A to nation B, and its value changes because the actors on either side of that border have different institutions, there are different frictions, different trade restrictions that mean that the value of the asset on one side of the border in one property rights regime might be different than the value of that asset once it crosses the other border. The second outcome that we're thinking about is called value compression. And here we think about the spatial extent of a resource as it moves under climate change from one place to another might change. And if that changes and the resource becomes more scarce, assuming that you have the same number of vessels fishing for, say, that fishery in a smaller space, the value contained within that fishery might just happen in a closer area, which might lead to more vessel interactions, and that could potentially be a precursor for conflict. So we think both value asymmetry and value compression are two important frames for thinking about the reallocation of natural capital under climate change and why that might be important for conflict. I don't think I need to motivate why oceans are important to this group. These are folks who are giving up a lunch hour or coming to listen to a webinar at 1 o'clock or watching online because they're interested in the sustainable management of marine resources, not just in the UK, but hopefully around the world. I think that now is a great time to think about the ocean, particularly because we're in the middle of the UN Decade for Ocean Science for Sustainable Development, and there are a number of reasons why studying the ocean now is critically important. I think about sustainable management of oceans in a particular way, and as an economist, I think that the way that we manage oceans sustainably can be viewed, I'm not going to put a normative frame on it, but can be viewed through understanding something like non-declining ocean wealth. I argue that we should manage the ocean at least as well as we might manage a bank account. And if we can understand how to manage ocean resources in a way that the balance in our account doesn't decline over time, we might think about that as one idea or indicator for sustainability. And indeed, the United Nations High-Level Panel for a Sustainable Ocean Economy writes that changes in ocean wealth are one of the most important indicators of sustainability. So how do we measure ocean wealth? We can't just go to an ocean accountant. We have to think about the change in the balance sheet of ocean assets. And that then means that we need to understand what ocean assets are. So capital assets, and the way that I'm going to talk about capital today, are things that store wealth and enable future consumption through the production of goods and services, or the provision of goods and services. Healthy fish stocks allow for future populations to consume the ecosystem services provided by fish in the future. Ocean assets then are capital assets, manufactured, natural, social, that are within the marine and coastal economy. We can think about some of them as produced, and produced ocean assets might be within the production boundary of the economy and include boats, oil rigs, port infrastructure, and tinned sardines, but also managed fisheries. And non-produced ocean assets are things like wild-caught fish stocks, coral reefs, and deep-sea minerals, things for which we often lack prices. And so if we want to make sure that that balance sheet of ocean assets is non-declining over time, we might want to think about how we price things that we don't have market prices for, and how we can measure the change in the value of those assets. One way to measure the change of the value of an ocean asset is to look at a particular stock level. And so here I have a horizontal axis Q for quantity of some ocean asset stock. And at time t, we have quantity S. At time t plus 1, that quantity is now reduced to st plus 1 by some amount. So we've reduced the quantity of an ocean asset. Off the bat, that's a change in a physical measure of the asset. And we might think that that's a threat to sustainability, that the quantity of the asset has declined. But that might not be the whole story. And indeed, there are lots of things that decline in quantity, but don't threaten notions of sustainability. We have fewer horse-drawn carriages today than we did years ago. That doesn't mean that the transportation sector or the horse-drawn carriage industry is potentially less sustainable or less supporting of human well-being. There might be efficiencies that have changed over time or new technologies. We can estimate the shadow price of a population of fish, and we can multiply the quantity by that estimate of the shadow price and get a change in wealth, which is represented by this red square. And that's one way of thinking about a change in the value of an ocean asset. Now, that estimate of the shadow price of fish can come through a bunch of different methods. We can use the market price of fish as one indicator of the shadow price of fish. Here, the shadow price I'm using is a term for the accounting price, or the asset price of, say, this population of fish. But that might not be the best unit that we want to use. And this is only potentially a good estimate if we can get it at one observation of the level of stock, and doesn't account for the fact that as that stock becomes more scarce, its price might change. And so if we were to only use this one estimate of an accounting price, rather than thinking about the change in that accounting price or the opportunity cost of extracting a unit of fish, as we move from one regime of high stock to another regime where we have lower stock, we might underestimate the value loss from that reduction in stock due to ignoring this change in the opportunity cost of extracting fish, or the accounting price of that asset, under increasing scarcity. And so this yellow triangle represents potentially the underestimation that we might have if we only use the red box to estimate the change in the asset. So the general idea is to pick up on work done by Eli Fenichel and Josh Abbott, an approach to capital asset pricing for nature. And the general idea I'll walk through quickly so I can get to some of the later results. But the idea is that we observe an index of the flows of net benefits given some stock of assets. And the value of that stock of assets is just the discounted sum of the future flows of benefits from that stock. So this is essentially the net present value of the future flows of benefits from a healthy population of fish. The asset price then for that stock of fish is just the change in that value for a change in the level of the stock. The market price of fish is a different number, so that's going to represent the benefit flow from extracting a unit of fish, not the asset price or the opportunity cost of extracting a unit of fish from the water. Why? Because we know that if we leave a fish in the water, it could potentially make more fish in the future, and there are important ecological dynamics that we have to consider that might feed into its future value. So we can think about defining the stock of an asset, how that changes over time, an economic program of use that describes resource extraction, an index of the net benefits, say from selling the fish at market, flowing to society at some time, how the stock grows, how humans impact that stock through fishing, the present value of net benefits through time, an accounting price, and a discount rate. And if we have kind of this set of parameters, we can think then about manipulating this value function, rewriting it in a couple of different ways, using some calculus, which I'll skip through for the moment, to get to an accounting price, P, as a function of 4 objects. And I'll talk about those 4 objects in a second. But it's the partial derivative of the flows of net benefits with respect to the stock, P dot S, which is the time derivative of the accounting price, which might represent something like the capital gains. And then in the denominator, a discount rate and the marginal impact on the stock level from adding an additional unit of stock. This formula on the bottom that comes from this Fenichel and Abbott paper in 2014 looks almost identical to the result from Dale Jorgensen's 1963 paper, Capital Theory and Investment Behavior, which is to say that looking at this from the lens of a bioeconomic system delivers something that makes sense to economists that think about asset prices in capital markets. And that's the item on the right. So there are direct parallels between the terms on the left and the terms on the right. What does that mean in practice? It means that we can approximate the unit price of capital stored in an ocean asset like fisheries by understanding or gaining information on 4 items. The first is the change in net benefits with respect to stock, which is the top left. On the right is the time derivative of the asset price, which is just a function of the asset price that we have on the left-hand side of the equation. Again, that represents capital gains over time. You can think about how the asset price might be a function of expected changes in the asset price in the future. In the denominator, we have a discount rate. We can think about 3%, or if we want to follow the OMB's new circular guidance, we can use, say, 2%. And then on the bottom right, the marginal change in the asset stock dynamics, say from fishing or from the growth rate. So then we can move to see how to apply this framework to understand changes in ocean ecosystem wealth, thinking about case studies from the Pacific. And so here in this map, you can see the exclusive economic zones for different nations and territories in the Pacific that give you an idea about all of these different boundaries that might be helpful to think about in terms of that value asymmetry or value compression, and how climate change, changing an ocean temperature gradient or habitat suitability for different populations might be really important in an area where all of these exclusive economic zones are on top of each other, like the Pacific. So I'm going to first show an application to the US Hawaii longline big eye tuna fishery. And this is work done by a bunch of folks led by John Woodill, one of the postdoctoral scholars that I mentioned at the beginning. We're going to take a parameterized model of a 2-actor fishery, and we're going to later think about how to parameterize a 2-actor fishery for the reef fish in the Gulf of Mexico. And these are the parameters that we're going to use there. But before we do that, we're going to, so these are the parameters that come from this Fenichel et al. Paper that estimate an accounting price for reef fish. This is our application to the Hawaii longline big eye tuna fishery, where we can come up with an asset price curve for big eye tuna. And once we have this asset price curve, when we approximate it by calibrating a model of a fish assessments with market price data and cost information, we can get this asset price that gives us, for the 2018 total stock level for longline big eye tuna, a price of, say, almost $9,500 per ton at the stock assessed level of 655,000 metric tons of tuna. And we can ask, given this price curve, is this a well-managed fishery? We know here the stock is above maximum sustained yield. but we don't know anything yet about the wealth stored in the fishery. This is just a snapshot of the price curve from 2018, and this is only going to represent the market value of fish and not going to include potentially all values associated with the fishery. We can repeat this exercise over time and get different price curves at different stock levels from 2010 to 2018. And then we can map out what the book value or the balance sheet of wealth stored in the Pacific Big Eye tuna fishery looks like in terms of like a lower bound capturing only the market value of the fishery. Looking at this, the important thing to notice is that we're going to think about changes, not totals. So this is a relatively stable account of ocean wealth stored in this Hawaii longline Big Eye tuna fishery. Over time, the value has fluctuated somewhat, but over these 8-9 years, the total asset value of the fishery has appreciated by, say, $600 million. And so that represents successful fisheries management, perhaps, or at least that there's not a loss in wealth stored in fish as captured by the market value of fish through time. Then we can move on from this example, applying it to a one-stock case, to thinking about a one-stock, one-actor case, to thinking about a one-stock, two-actor case. And this is where the project and the inspiration for thinking about fish wars comes from. So I showed the map earlier of the Pacific and the exclusive economic zones. What I'm going to show here is a paper by Mendenhall et al., which is co-authored by one of our collaborators on this project, that shows how the percent change in maximum catch potential by 2050 might change in that time horizon, where the redder areas are going to have lower maximum catch by 2050. The bluer areas at the extremities there are going to have higher potential changes in maximum catch, or increases in maximum catch by 2050. The circles superimposed on top of this map represent MIDs, or militarized interstate disputes involving fishers or fishing vessels, from 1993 to 2010. And so we see these happening in areas already that we anticipate will have reductions in maximum catch potential through time, predicted out to 2050. So some of these areas in red already have a number of incidents of militarized interstate disputes, and we think that that could be exacerbated by changes in the distribution of fish. And the magnitude of the value asymmetry, or the shadow price or accounting price of fish on either side of those boundaries, might help us understand the economic pressure associated with these fishing constraints imposed by climate change. So again, these are the two frameworks, the two ideas that we're looking at this problem through. And what we're going to do is take that initial theory that I laid out very quickly, that looks at the opportunity cost, or the shadow price, or the accounting price of a unit of fish. And now, instead of thinking about the social value or the social opportunity cost as though this fishery value accrues to all of society or one actor, we're going to think about multiple agents that are operating over a shared resource, like the tuna fishery, or as we'll discuss later, like the Bering Sea and Aleutian Islands pollock fishery. Here then, we're going to have at the top different flows of net benefits accruing to different actors. Actor A is going to get one flow of net benefits from a shared stock S with its own economic program of resource use. Actor B is going to have a potentially separate flow of net benefits from a shared resource stock S under its own set of resource use program, under its own resource use program, excuse me. In the denominator, both countries here are going to have the same discount rate, but they could have different discount rates. That could be informed by different countries' standard practices. So in the UK, for example, we have guidance from the Green Book about long-term social discounting. In the US, there's different guidance, and so countries can have different discount rates that they apply for thinking about long-term planning and the value of long-term investments. And then the overall stock dynamics, since it's one population modeled here, are going to be governed by one kind of biological or ecological growth function. And then the sum, or here subtracting from that, the extraction of fish due to actions by country A and actions by country B, where these two countries aren't going to interact in this first model except through their shared resource stock. So they're not behaving particularly strategically here. They're just reacting to the level of stock that they observe, but the overall level of stock is going to be responsive to each country's decisions about how much to fish. Future extensions are going to look at how multiple agents and multiple stocks might interact, where not only do you have different behaviors from different actors, but you also have predator-prey interactions or different ecological dynamics across different stocks of natural resources. Thinking about heterogeneity in the value of natural assets is something that I've worked on for quite a while now. I've first looked at how different institutions and different resource endowments might lead to differences in the value of natural capital, thinking about groundwater in the state of Kansas. And so if institutions are the same and resources are the same, then we might not expect there is no heterogeneity to drive variation in relative scarcity or the opportunity cost of extracting a resource. If you have the same institution with different endowments, you might think that the law of one price might hold, except that high transactions costs for moving or reallocating natural capital through space. Moving a sewing machine is much cheaper than moving large amounts of water from one place to another, means that the importance of the spatial distribution of resources across space is really critical to determining the opportunity cost of that resource use. Using resources in a relatively scarce environment compared to using resources in a relatively abundant environment of resource density have different implications for opportunity cost and result in different asset prices. Those then inform different management decisions and have different implications for sustainability. If you have different institutions with the same endowment of resource, you might get different asset prices. And here there's a picture of, say, forest management across an international border on the island of Hispaniola, so between the Dominican Republic and Haiti. And that is exactly the case that we might think of when we think about a fish moving across an international border and having a different institution applied to that fishery management, driving differences in the opportunity cost of resource use and in its value as part of the balance sheet of ocean resources for the planet. As an example, we showed that different institutions and different resource endowments result in different shadow prices or different accounting price curves for water in the state of Kansas. Areas that had different amounts of water, and here each of these lines represents a different water management district in Kansas, resulted in different asset prices for the water in each of those different areas. And the important note to take away from this figure is that if we just did this at the state level, we get that middle curve that's in red. But if we were to do it, if we were to look at asset prices or the opportunity cost of extracting a unit of water in different areas, you get this large spread, right? Almost a 100% higher opportunity cost potentially for the same endowment or the same stock level of water in region 1 compared to, say, region 3, region 2, or region 4. These differences then mean that coming up with a statewide policy, if we're not going to have spatially explicit management opportunities, drives a wedge between understanding the opportunity cost of an average endowment of the resource with an average institution applied to it, compared to aggregating the asset prices across each of these districts separately and coming up with an average of the asset price curves rather than the asset price curve for the average resource under the average institution, right? So this means that the way that we aggregate these values across space can matter and can matter consequentially for how we think about managing resources. This was a rather static example on land and didn't have this change over time of resources that we might deal with in a marine environment in the same way. And so this bottom left-hand corner represents the fisheries example that I'll discuss now. So we're going to look at the Gulf of Mexico reef fish example that was in this 2016 Fenichel and Abbott paper and reproduce the accounting price curve for the Gulf of Mexico reef fish fishery. Through these figures, we're going to simulate asymmetric changes in the economic environment across different countries that share a stock of fish. And so we're going to imagine country A and country B, and we're going to think about the asset price curve for both of these countries under changes in the economic environment. Here, throughout, we're going to have a dotted line that represents a baseline case of the one actor example. So this is our baseline with one actor managing the fishery with kind of a social accounting price curve for that one individual. If we then move to thinking about two symmetric actors, so now this Gulf of Mexico fishery is managed or is fished by two different countries. You could imagine the US and Mexico having two separate fleets, for example. Or you could imagine two different states potentially managing different fleets or two different companies. There are going to be two symmetric actors, so the actors look identical and they're going to exert the same total effort. And so here on the x-axis, we have the stock size, the tons of fish in the fishery. On the y-axis, the shadow price or the accounting price, or again, the opportunity cost of extracting a unit of fish at each of these different levels of stock size. And what's important about these asset price curves, again, is that if we move from one level of stock to another level of stock, it's the area under that curve that tells us the change in wealth that results from that loss of fish stock. And again, how curvy that this price line looks is going to tell us how much we might underestimate the wealth loss due to the effect of scarcity on that opportunity cost or asset price. So here, when we move to the case where we have two identical actors putting out the same number of vessels or crew hours fishing for reef fish in the Gulf of Mexico, there's going to be a lower asset price. So the opportunity cost of fishing for each country becomes lower when there are now two actors competing for the same resource, even though they don't have strategic behavior in this model. So the two-actor case shifts these asset price curves down, which means that the wealth consequences for each of the actors is going to be lower than if there were only one actor for a change or a reduction in the stock. But now we have wealth consequences for two actors. If we double the costs for one country, we see a decrease in the marginal net benefits of fishing a unit of fish for one country only, country B. This doesn't impact country A. That solid line in reference to the dotted line, which is the one actor case, stays exactly where it was from the previous example. And so there's no change to country A when country B has higher costs of fishing. Now, this makes sense. The impact only affects one country in terms of its marginal benefits from fishing, and there's no strategic interaction. So they're only going to interact through the stock, and costs on one country aren't going to manifest through the system. So country A has no change from the symmetric case, and country B's asset price curve shifts even further down, and that's the dotted line, the dashed line. If country B then has a reduction in technology, so let's say that the fishing technology for country B, or the efficiency of catch from effort in country B, is only 90% that of country A, relative to the previous case with everything else identically the same. What's interesting is that increase in efficiency means that for the same number of vessels, or the decrease in efficiency for the same number of vessels, country B is catching less. So country B is going to put more vessels out on the water potentially to maintain the same level of catch at a particular stock level. Country A is then going to shift up from the symmetric case. So the asset price curve increases for country A when they had this comparative advantage in technology. Country B's asset price curve shifts even further downward. And so here, again, even though there isn't any strategic interaction, the price curves between the two countries diverge, and you get this value asymmetry generated from a change or a difference in technology across two different countries. Again, we can think about this baseline case where there's the same joint effort. This is our touchstone. The dotted line is the baseline with one actor. Here, the solid line are both countries when we have two symmetric actors. And then we can look at a change in effort from country B Again, those price curves diverge. Country A moves up, country B moves down when you have a change in effort. And so technology and effort here are operating through the same channel. Even though there's not a strategic interaction, the efficiency of resource use means that the opportunity cost of extracting the resource in one country increases, given a particular stock level, and the opportunity cost of resource use for the country with the lower efficiency decreases. This is exacerbated under lower stock levels. And so the difference to the dispersion between these two asset prices is lower under lower stock levels. This shows that scarcity could potentially drive further value asymmetry with different distributions of fishing behavior and characteristics across different countries. Now we want to move to advancing just thinking about a two-actor fishery where there's no strategic interaction to thinking about how conflict might enter into this conversation. So we're going to think about conflict here first happening below a particular threshold of stock. This builds on work by Yukiko Hashida and Eli Fenichel published in the American Journal of Agricultural Economics in 2022. The paper is called Valuing Natural Capital Under Periods of Inaction. And here we're going to set S lower bar as a threshold below which conflict might arise in a fishery. And this relates to the Hashida and Fenichel paper in that in this example, we're going to want there to be a point at which conflict bites and changes behavior, but other places where conflict doesn't impact behavior. Here, conflict outcomes might increase or decrease resource extraction in fisheries, and the literature has plenty of examples where conflict outcomes increase resource use, driving the need to feed people or the need to supply a country with resources from the ocean, or conflict could reduce the amount of effort or the catch accruing to different actors, decreasing resource extraction. In fact, the history of predator-prey modeling comes from thinking about fisheries under resource use, and that was Umberto d'Ancona and Vito Volterra thinking about fishery resources in the Adriatic. So here we're going to think about fishery in a conflict state where only one country responds in the conflict state by getting poorer returns from its effort. So they have the same number of vessels they would otherwise have on the ocean, but those vessels start fishing more inefficiently, not going to the areas where they think they can catch the best fish, but going to areas where they might think they're the safest or might avoid conflict, or avoiding areas altogether because of the risk of conflict. We're going to assume, again, that same amount of effort, vessels, crew hours, et cetera, spent with just lower returns to the effort invested. In low stock regimes, conflict is going to make less of a difference. In high stock regimes, conflict's also going to make less of a difference. So in low stock regimes, countries might have a larger need to catch. And as a result, we also want to make sure that countries aren't fishing negative fish. And so we want the returns to effort at low stocks to go eventually to zero when you have zero fish. So you don't want to be able to catch negative fish, and this is something that we want as a nice mathematical property of the conflict model. In high stock regimes, when fish are more abundant, the conflict pressure might not actually matter for how efficient you are at fishing because fish are everywhere. And so again, it's a nice mathematical property that addresses this value matching smooth pasting condition that allows us to get this price curve in the model. So here, as an example, country B in a conflict state, here the blue line, where the conflict state is independent of stock and is always on, is going to have lower catch at different stock sizes relative to country A, which is exactly identical to country B, except that in country B, the conflict state gives them lower returns to catch at different stock levels. And as I mentioned, on the left-hand side, under scarcity, these two lines are going to come together. We don't want that blue line to dip below the x-axis. We don't want there to be negative catch for country B. So here's our benchmark, and what happens? Country A, the opportunity cost of fishing shifts up relative to the symmetric case. It comes closer to that, you can think of one social planner case or one actor case of resource management. And country B's curve has a large shift down. There's a low opportunity cost of resource use in country B, where there are fewer returns to catch for a given stock level. And so here, the conflict state drives a large difference in the asset prices, driving large value asymmetry in the system. We can think about conflict that then gets induced only below a certain threshold when there's relative scarcity. And here, conflict turns on at 2 million metric tons of fish. At 2 million metric tons of fish in the Gulf of Mexico example, we're going to turn on that conflict regime. And at that point, these two lines are going to diverge, and country B is going to catch fewer fish for an investment in effort. When that happens, again, here's our benchmark case. We don't really see the same dispersion in asset prices. There's almost no change from the symmetric case between the asset price curves for country A and country B. And so when that conflict regime kicks off, and whether that conflict regime is motivated by resource scarcity or motivated by potentially geopolitics or other interests, could mean very different outcomes for the opportunity cost of fish changing from place 1 to place 2, and also different motivations for value asymmetry or opportunity costs from resource use that might induce potentially illegal, unreported, and unregulated fishing across borders. If we have a conflict state that happens under scarcity, but there are added costs to country B. So country B is not just in a conflict state where they get lower returns to fishing, but each unit of effort now costs country B more, and here twice as much as country A. When that conflict regime now turns on, we can start to get that value asymmetry when additional costs are imposed, but not just through inefficiencies relating to this catch model, where in the scarcity-driven conflict state, country B isn't able to fish as much as country A. Finally, we can rank order all of these different scenarios and think about how value asymmetry manifests in these simulations for the Gulf of Mexico reef fish. Always conflict, so being in a conflict regime regardless of the stock level, generates the largest gap or magnitude value asymmetry in the system. Changes in technology and effort come second, but are a distant second. Additional costs on a scarcity-driven conflict regime come third, and that's the yellow line. The orange and red lines are costs and scarcity under a conflict regime. And finally, the symmetric case is the horizontal axis, where there's no difference between the shadow prices of country A and country B. So here, I've walked through a couple of different simulations for this Gulf of Mexico fishery, where we have different characteristics of country A and country B, each taken in turn to understand how these asymmetries across the economic environment or actor characteristics might drive value asymmetry. And with the understanding that the gap between these shadow prices, these accounting prices, the book value of fisheries as they move from one place to another, might be one way to measure the likelihood of conflict. We can then take this to the Bering Sea and Aleutian Islands pollock fishery. And so here is a map of fishing hours by US vessels and by vessels on the other side of the border by Russian vessels. So the red dots represent Russian vessels, the blue dots represent US vessels, and you can see that there is this regime where, particularly in some areas, there might be fish that straddle the EEZ, and there might be examples of, say, value asymmetry that happen from one place to another with different fishing behavior, with different costs, with different technologies, but potentially also with different conflict regimes, which here we think about as effort that's already deployed that returns fewer units of fish per hour fishing. This is the future work that I'm previewing. So this is Pedro Barros's work, a postdoc with us here at Exeter who's brilliant, and he's put together an estimate of the accounting price for Alaska pollock in 2012, looking at the entire fishery. And so that at the 2012 stock level, he's estimated an accounting price of $573 per ton. He's done this using time series, but also using a panel method that exploits spatial heterogeneity and spatial variation in fishing patterns. And again, those numbers are very similar through time. with these two different methods in 2012. And then he's generated again this balance sheet for Bering Sea and Aleutian Islands pollock that shows that the fishery largely over this time period from 2004 to 2021 has increased in the value stored within the fishery. Another way of saying that is that the fishery has been well managed by the Fisheries Council. Then we can plot the accounting price versus the market price for fish. And here the book value is greater than the market price by about $200 per ton, which means that the opportunity cost of extracting another unit of pollock under the current management regime is higher than the market price, right? We want to then move to thinking about modeling the Russian fleet as compared to the US fleet and thinking about characterizing that value asymmetry across that border in order to understand where and how conflict might arise due to differences in the value of fisheries to different nations. So the consequences of this multi-actor natural asset pricing approach advances over this one-actor case to think about how different policy responses to climate change might result in spillovers beyond these international borders, resulting in changes in ocean wealth that again might not be zero-sum. These systems are governed by ecological dynamics and they might be highly nonlinear, which means that small magnitude changes might result in large wealth shifts. Notice in that figure that I showed from the final Gulf of Mexico case that compared the difference between the asset prices in country A and country B in a ranked order, that's on the bottom left here, the largest gaps between country A and country B's accounting price occurred at low stock values, low stock levels under lots of resource scarcity. Finally, the dispersion in asset values mean that if we transfer a unit of stock via different temperature changes or ecological pressures that move fish from one place to another, the gap between different countries' asset prices might mean that a loss of a lot of value in one fishery by one country might manifest in a gain that's orders of magnitude smaller to the other country. And so one country is harmed by the reallocation of resources in excess of the potentially the capacity of the country that gained the resource to compensate them for that loss. This means that there might be arbitrage opportunities or incentives for conflict. And we might think about then moving to a continuum of actors operating in this space, not just two actors, which would be closer to the reality of, say, fishing on the high seas and fish moving across many EEZs, as we saw in the Pacific case. So I'll leave with that a beautiful picture of the ocean from the other side of the planet from where I'm on that shows not so much land, but highlights the importance of the oceans as a provider of well-being, a food source for billions, and something that we should pay attention to in this decade of ocean science and sustainability. So thanks so much and look forward to taking some questions in the final 10 minutes here.